I do only have roughly order 5 slides to this. So I wanted to introduce very quickly semi-empirical methods just so that you know what this is all about. And the basic approximation that you make here is essentially to take 2 electron integrals and assume, basically, if I label these basis functions as having an atomic center as well as some other label that's just a dummy index, then whenever 2 basis functions that are building one of the charge densities are not on the same atom, then this whole thing goes away. And they're all, so essentially what happens is that many of these 2 electron integrals, these Coulomb integrals, are thrown out. And there are various levels of sophistication to this. But what's important to realize is that that makes it sound like, because then you do a Hartree-Fock type of self-consistent field using this approximation. And that makes it sound like this is an approximation to Hartree-Fock. But that's actually not, it's more complicated than that because you end up parameterizing all of the remaining integrals. That is, they have values that aren't quite the ones you compute in order to try to cancel out the errors that you're making. And so what this really means is that semi-empirical methods are oftentimes it's hard to know when they're going to work in advance. And basically you have to, even more so than anything else, when you deal with semi-empirical methods, you have to know that on related systems this has worked, right? And then that's basically what lets you, gives you some confidence to proceed. And that's just because people don't really understand very well how it is that the parameterization offsets the errors, basically the onslots. But what you want to know is that it's going to be much, much cheaper than even density functional theory. And so this is going to be cheaper than Hartree-Fock by orders of magnitude. And you can actually also do a lot of the tricks that people try to do of linear scaling and so forth in Hartree-Fock, and density functional theory can be done in this context as well. So they're formally and cube scaling as well because of the diagonalization, but it ends up being much faster than that. You can almost do proteins with semi-empirical, actually you can do proteins with semi-empirical methods and optimize geometries. It's horrifically difficult. So it'll take days to do it, but you can do it. There are many variants of these, and which I just gave you acronyms so that you know. And basically, the advantage, I guess I said this already, that they're basically cheaper than DFT. They're really the only truly viable quantum mechanical-like methods that really look like quantum mechanics that you could do for entire proteins. And this again will change, in 5 years or so. But right now, you can't quite abandon force fields for this, but you could start to entertain it. And the other thing that is sometimes overlooked is that you can actually reparameterize them for particular processes. So if you have some semi-empirical, some particular reaction, for example, inside an enzyme that you want to model, and you know that the semi-empirical method is not doing as good a job as you want, but you know better answers from high-level quantum chemistry, then you can actually start tweaking the parameters of the semi-empirical method. And as long as you tweak it, there's a number of people have done this, and as long as you make sure that you don't change things very much, then you can have quite a bit of success with that. So you can actually basically use this as a way to have a very finely tuned low level of quantum mechanics. The disadvantages are that the hydrogen bond strengths are really, this has really been a sore point for semi-empirical methods for many years, and every new revision, there's really 2 things that people try to fix. One is hydrogen bonding, and the other is transition metals, right? That's the only thing, basically all of semi-empirical development for the last 10 years has been about that. And not a lot of progress has been made in hydrogen bond strengths. Some, but not by an order of magnitude. And it's still expensive compared to force fields. So the summary really of all the methods, not including semi-empirical, so these are really all the sort of ab initio methods, is given here. You have the restricted Hartree-Fock, unrestricted Hartree-Fock, the CAS-SCF, configuration interaction, couple cluster, MP2, and density functional theory. And you can just see whether they're variational or not, which is really, it's important to know if the method is variational, then presumably as you do better and better, the absolute energy is getting lower and lower, and it never is going to go below the right answer. And if it's not variational, you better not be using that as a criterion. So it's important to know to know whether it is or not. Whether they're multi-reference, almost all of these methods are not multi-reference. It's only the CAS, SCF, and CI that are, and that means that these are really the kinds of methods that are good for bond breaking, for structure. The other single reference methods are just as good as multi-reference methods, near equilibrium geometries. Size consistency is this issue that we talked about a little bit. And finally, what you really probably care about, what would be the approximate error in a 10 kilocalorie per mole barrier height? This is just sort of out of my empirical database, right? So sort of just some range off the top of my head, if you want, but it's basically correct. For a restricted Hartree-Fock, you would basically be off by up to a factor of 2 on this barrier height, and a restricted Hartree-Fock would not improve it very much. CAS SCF would bring this down to something between 3 and 7. Some sort of CI, multi-reference CI built on CAS would bring it down somewhere between 1 and 5. Couple cluster would typically go down even lower to something that was actually getting to a 1% error. And the density functional theory would typically be around, this is a hybrid type of technique. So the best density functional you could do B3 lip would be somewhere around 1 to 5 kilocalories off. And this is the kind of, you can basically count on being in that range, scale it appropriately. There are multi-reference perturbation and couple cluster theories that I didn't actually tell you about. And sometimes they've been successful, but they're really quite artsy still. Mostly people who don't write code wouldn't do it. But that may change. Hey. All right, and so now I need to start talking about to talk just a little bit about what you might do with all of this. And here I give you just a schematic so that I can show you something about the topography of potential energy surfaces. And just remind you that there are various minima, and some of these are global minima. There's one global minimum. And then there are many local minima that are just above this. And then the other important points you might care about are these sort of transition states between a minimum and some other possible minimum. And finally, this is a special thing. I'm sure you notice there are 2 surfaces here. Typically, if you were thinking only of the ground state, you wouldn't have this top surface here at all. And you would just be thinking of, for example, a transition state here and so forth. But if you have multiple electronic states, which is something we'll talk about very briefly later on, then you can have actually points where the 2 electronic states actually are truly degenerate. And these are important because in any sort of photobiology or photochemistry, essentially it's these points that are going to dominate. They're going to act like transition states on the return from the excited state down to the ground state. And so they're just they're very different from transition states though, because they actually are, they're peak, there are derivative discontinuities there. But this is just to then get to the next point, which is really that normally when you optimize the geometry, so after you have some electronic wave function and now you start moving the molecule around, what you're trying to do is to make the derivative of the energy with respect to R 0. And normally you may think you're looking for a minimum, but this is really what you're doing. And so the geometries that you find could be local minima or global minima or transition states or higher order saddle points. And this is actually an important thing to be aware of, that you might find what you think is a minimum, but it may not be a minimum. I mean, how do you check? I think you all know this from calculus. Basically, you just build and diagonalize what is called the Hessian matrix, but basically just the force constant matrix, or the matrix of second derivatives of the energy. And typically, for most methods, you can build this, and then you just diagonalize it, or actually the program does this for you, right? You just tell it, please do this, get the force constant matrix and diagonalize it for me. And then you count how many negative eigenvalues you have, and 0 is the local minimum, not necessarily the global minimum, but some sort of local minimum. 1 is a saddle point, and greater than 1 is useless, because that means it's some higher order saddle point, has multiple directions going down to connecting not reactant and product, but reactant with other reactant, with product, with other product. Now, one of the things you want to be aware of here is that this Hessian matrix is typically built in Cartesian coordinates, and actually almost invariably. And so it's going to have 6 zero eigenvalues that correspond to rotation and translation, and you've got to find them and ignore them in the analysis. And how do you find them? Well, some programs will attempt to project them out, but usually, basically, you can take programs like Molden, which you actually use today in the lab, And it's very easy with these programs to animate the normal modes and do essentially this, what we're doing here, basically just look at the eigenvectors corresponding to that force constant matrix. And one of them will actually just have the molecule spinning around this way, and one will have it spinning around the other way, and so forth and so on, and then you can tell. Right? The reason that because actually you should all look at me and say, well, what are you talking about? They're all going to have 0 eigenvalues, so I can find them all very easily, right? Well, there's numerical error, and so you actually will often run into the case where you don't really know how big is my error in the frequencies, and which ones are the rotations, which ones are the translations, which ones are low frequencies that maybe should be imaginary, corresponding to a transition state. And that's actually a good way to get a handle on how much error you have in the frequencies, is by what the spread is at the low end for the rotations and translations. So if those are off by, if those are spanning the range, from 20 imaginary wave numbers to 20 wave numbers, then that's telling you essentially that none of your frequencies are really more accurate than that, so you should know that. The disadvantage to doing this is that it's pretty expensive. It's about 10 times an energy calculation, so you may or may not end up doing it routinely. But the special warning that goes along with this is that whenever any molecule has symmetry, then you have to be very careful when you're looking for minima that you actually optimize to saddle points. It should be obvious that if you enforce symmetry, you're obviously going to maintain symmetry. And so if the minimum has a different symmetry, then obviously you're not going to find it, right? So I don't think anybody would have a problem understanding that. But what you need to understand is that just starting from a high symmetry geometry is enough, because the symmetry then requires that the gradients are non-zero only with respect to totally symmetric modes. In other words, you can't break symmetry with the gradient. And the only way that an optimization will break symmetry is through numerical noise. And so if you start, and you can actually do this, maybe you should probably do this today. Take the geometry of water, start with a perfectly linear molecule for your initial guess, and then go and optimize it, and then go tell your friends about how you just discovered that water is actually a linear molecule in the right? So, well, or don't actually tell your friends, but that's what you'll find. And so this mistake is made over and over and over again in the literature. It's really kind of annoying. So you need to be aware of that. The conclusion here really is that if you can't always verify that your stationary points are minima by doing the Hessian because it's expensive, then at least perturb your geometry and see whether it comes back. Right? Perturb it by 10 degrees, break it out of symmetry, or by 0.05 angstroms is usually enough in bond lengths, and 10 degrees in angles. And avoid high symmetry starting points. You should always let the molecule find symmetry for you instead of starting from symmetry, which is actually often your tendency, is to start from symmetry because you think, oh, my molecule is flat. Right? Some dye molecule, it's flat, so why don't I just start with symmetry? It'll make the calculation much easier, but it also puts you in line to make errors like this. So, okay. Intrinsic reaction path. This is another thing really to talk about. Actually, I think Klaus sort of talked around this with steered molecular dynamics, where we were trying to find something that's sort of the analog of this, but a dynamic ensemble average of these. But the intrinsic reaction coordinate is typically just, it's exactly going from reactant to product in the minimum energy path. It's also called the MEP. And you can actually find these, if you can find a transition state, then you can actually ask a program to calculate this automatically, and it will go and calculate going forward and backward, and it'll calculate this path. And the only thing I really want to make sure that you understand is that this is relevant, really, and I think you probably should understand this from Klaus's talk, that this is relevant only if all the kinetic energy is drained instantaneously from the molecule at every point in time, which means that actually this is never really the right thing. The right thing is always something that is some moving around it, right? And which it really brings out the point that when you start thinking of really large biological molecules and some reaction happening inside it, that transition state, which may be well-defined, in other words, the reactant and product may be well-defined in the gas phase for this reaction that's being catalyzed by an enzyme, but inside the enzyme, there actually are many, many, many transition states, and it's some sort of average over all of these that matters. And so you should beware to read too much into this, right? The barrier height here, for example, the average may not be that. The average, the paths may actually all cut the corner, right? So forth. Okay. So, So now the question is, how do you make the molecules larger is really the question than what we've done so far. And what we want to do, before we do QMMM, we want to do the simpler thing, which is just to make them larger by, I don't know, a factor of 2 or 5, right? So now we can get maybe up into 500 atoms, maybe 1,000. So how can we do that? There's really two things that you can do here. Actually, what I'm going to tell you is you can use in two ways, either to increase the accuracy of the techniques or to increase the size range. And the way to do this is to go back and remember this silly two-dimensional graph. And say, okay, well, so electron correlation basis set 2, and here's the right answer. Well, is there another way that I could extend this graph, right? Is there something else, some other axis I could put on it? And in here, what I'm really going to ask is there a way to estimate the exact answer? Is there some way to extrapolate it? And the one hypothesis that I might come up with is that the effects that come from increasing the flexibility of the charge distribution are somehow physically separate from the effects that come from dynamic correlation. Right, now, this is not true. Okay, so there's no way that this is true, but it may be it may be close enough to true. And what it's really saying is that those two axes on the cannon, maybe I can treat them as though they were really independent, right? That if I went to one side and to the other side, that I could somehow extrapolate the corner point that I need. So this is, as I said, this implies that electron correlation and the flexibility of the electronic wave function are independent. Not only is this not true, it can't be true, because how easy it is to describe dynamic correlation must depend on the flexibility of describing the one electron distribution. So, but in any case, we proceed anyway, right? And say, okay, well, we're warned, but we're going to do it anyway. And the example here are actually two techniques that are you can even run these in Gaussian just by typing G2 and CBS. I mean, so they're actually quite well benchmarked and available pretty easily. And what they do is they take the extrapolated energy to be the energy of Hartree-Fock in a small basis set. That's the energy at the here. That's the energy here at this Mickey Mouse part of the cannon, right? And then they compute the correlation energy or some estimate of the correlation energy by going up in this direction. So I still have this small basis set, but now I include electron correlation. And then I go over in this direction and I estimate the basis set error, or the basis set effect, by computing the large basis set uncorrelated, right? And so then by subtracting large basis set Hartree-Fock minus small basis set Hartree-Fock, that's some delta E corresponding to increasing the basis set. And here I have small basis set correlated minus small basis Hartree-Fock. That's some delta E, or some increment, some decrease in the energy corresponding to correlating. And now I'm just assuming that there's no cross term at all. And so I sum all these things together, and I get, I simplify it by dropping out a few terms. I get this expression, which is supposed to be the extrapolated answer for the correlated calculation in a large basis set. Now, I mean, I wouldn't tell you about this except for the fact that it works. It doesn't work if you actually use, if for Hartree-Fock small basis set, you use a minimal basis set and you do something that's completely ridiculous, then it doesn't work. It works as soon as this level of calculation is semi-reasonable, which basically means double zeta or something along those lines, right? So when you get to 631 or 631 double star or something along those lines for this calculation, with Hartree-Fock even, then it will work. And the reason that it doesn't work with minimal basis set is because of what I told you before. Minimal basis set has no flexibility at all. You include all the dynamic correlation you want, you don't get anything from it because you have no flexibility. Right, so you need to have some flexibility so that you can actually adequately estimate the correlation effect. But you can read more about it in these papers, and actually in these papers it will actually tell you also the kinds of accuracies you can expect. And typically you can pretty easily get kilocalorie per mole accuracy in almost anything you want using that kind of technique. It's not necessarily the cheapest thing in the world, but that's why we want to shift now to trying to use the same idea in a different way. Instead of deciding that we want more accurate answers for the same size molecules, say, well, what we really want is to be able to do much larger molecules with similar accuracy to what we have already for small ones. And now what we can consider is a three-dimensional version of this canon, where the new dimension is some chemical dimension of model size or faithfulness. So water is some sort of a model for methanol, which is some sort of a model for isopropanol, right, and so forth and so on and so forth, right? And so you just keep on, these are all, and that's what you're basically seeing here. So actually I did butanol, right? So all of these, so if I imagine calculating the proton affinity, that is how much energy would it cost to pull off a proton here and create the methoxy and the NH+, then, you know, perhaps these numbers all have an intrinsic component, which is actually the same, and then some environmental component, which is a shift, right? And so if that was true, then I might be able to actually do the same sort of trick I just did, and I'll show you explicitly in a minute, but do that same sort of trick where this third dimension now that I'm going to move in would be the model itself. And so now the point that I want is is the corner of a cube. And it's the real system with the large basis set and the correlated energy. Now, this one thing I should point out is I've already set you up for that. You shouldn't really ask, when you try to play this game in the third dimension, you shouldn't ask really about the total energy anymore, because the total energy is going to be very different between this molecule and this molecule and this molecule, right? They're going to be, because they're going to be different just because of the Coulomb interaction of all these electrons with the heat of formation of part of butane, right? So that's a huge number, right? So you shouldn't really ask about the total energy, but you should ask instead about energy differences. And in fact, you never care about the total energy anyway. The only thing you ever care about is actually differences in energy. That's one of the reasons why quantum chemistry can work. So here you go. Here's our canon as a cube. This is the third dimension, which looks like a straight line, but it's supposed to be pointing back out. And here we go, and we get a student additivity. So we take well, this probably makes sense. What we really want is the real system in the large basis set with electron correlation, and that's going to approximately be the small model system with the small basis set with Hartree-Fock, which is this point down here, plus the correction due to the basis set increase, so small, large basis, Hartree-Fock, small basis, Hartree-Fock, plus the correction due to correlation, plus the correction due to changing the model from the small system, the model system, to the real system, right? And so each of these is just a delta E along each of these directions. And this works reasonably well. It's actually called IMOMO, or sometimes Onium, and it's Morikuma at Emory, who really was the original developer and champion of this. This is a paper that describes it that you can read if you want. The one thing that you should know about this is that it can be very sensitive to the choice of the small model. And that's really not any different from what I told you a minute ago, that if you try to do G2 or something like that, that is try to increase accuracy using a minimal basis set, you're not going to get anywhere, right? And the same thing is true here. If you try to use water as a model for, I don't know, whatever, decanol, decanol with fluorines on the end, right? You know, then it's not going to work very well, right? Because the perturbation is huge from the difference between the small system and the real system is huge. Fluorines pulling electrons out, sort of organic chemistry type of intuition. But basically, I mean, you may or may not have that intuition, right? And so what it really means is that you have to try different partitionings and different types of models for the particular system before you can really, you can't apply this as a black box. You actually have to think about it a little bit and try several model and high-level system, or model and real systems. So you can actually simplify this. If you just lump the basis set and correlation together and just say there's a high level and a low level, and the high level is some basis set with correlation, and the low level is some other basis set without correlation, then you can basically write it in this way, which is the same thing. The energy that you want of the high-level electronic structure theory method for the real system is approximately the low level for the real system plus the difference between the high and low level on the model system. And an example here, we'll actually do an example in the lab this afternoon on the proton affinity, where basically you'll go through that same sort of exercise for methanol and water. So this is just an example of, another example really of how this works, and this is from a paper of Morikuma's, where they were just looking at SN2 reaction. They actually have never, surprisingly, they never actually used this for a biological system. They've used other variants of it that we'll talk about later. But basically, what they did here was to take a several water molecule solvating a methyl chloride and hydroxide, and this is just going to do an SN2 reaction. So the hydroxide comes in and ejects the chloride or vice versa. And then they computed the heat of reaction and the transition state, the barrier energy for this, using the decomposition, where the real system included the reactant and product and also all of the waters around it, which was 4 in this case. And the model system just was the reactant, right? And the answers, this is the only reason you really want to know about this, that basically they got in the absolute energies, and this is actually quite amazing, but they got errors of about 2 kilocalories per mole per solvent molecule in the absolute energy. Now, the fact that it's 2 kilocalories per mole per solvent molecule shouldn't surprise you, because as you add more and more solvent, you're actually making this approximation over and over again, right? That there's an additivity. In other words, each solvent molecule contributes some stabilization that you're not getting in the model system, but you do get, or excuse me, in the model system, but you do get in the real system. And so any error you make is going to be additive in the number of solvent molecules. But as I said, that's actually the reason why you don't want to look at absolute energies here, but what you instead want to look at is the energy differences, because there they basically found errors of 1 to 2 kilocalories per mole in the energetics overall, right? So it was reasonable accuracy. And then the question is, well, did they do something that was sufficiently simplified that they actually won, right? That it was cheaper? And the answer is yes. So here, then that's what you see here. That basically the real calculation would have taken, actually you should look at this one, the real calculation would have taken 15,000 seconds, and they spent 1,600. So basically it's a factor of 10. It's about a factor of 10 faster for a toy system. Now if you actually start putting the more and more that goes into the model system, the more and more the speed up, if you want, right? The question is just always whether or not you can get away with the particular truncation. Okay, from here you can actually go to something else so along the same theme, so it's worth going through, which is trying to take transition states or reaction energetics and doing the same game, playing a multi-level game, where basically you're going to optimize with a low-level method and then do energies with a high-level method. The idea here is that you would find the barrier, you would find the reactant and the product, and then you would go, once you found those geometries, you would assume those geometries don't change, and you would do something at a more sophisticated level to get the energetics. Well, actually, that's not smart. It sounds smart, but it's not. And you can try to do, actually, you can figure out why it's not smart pretty easily. So why do reactions have barriers? They have barriers because of the electrons. So a simple Marcus-type picture, I just have 2 parabolas corresponding to 2 arrangements. So this is a toy example of H2 plus H goes to H plus H2, just because it's easy to draw. And then you can see that basically one of these curves, this parabola, is corresponding to what this x-axis is just moving that hydrogen in the middle between the 2, right? And I just want to know what the energy is for the spin coupling that has a bond between these 2 hydrogens and no bond between these 2. And clearly, as I move this hydrogen away, it goes up in energy. It's disfavored, right? And same thing is true for the other side, but in the opposite direction. And so I have 2 sort of parabolas, and they cross at some point. And if I put that into some Hamiltonian, then I have some Hamiltonian matrix, which has those diagonals that I drew, and then it has some off diagonals, which are basically the couplings between these 2 states. It doesn't really matter too much right now, because I'm just going to say let's just pretend those are constants, right? This is what they really are. They're these matrix elements, but I can just pretend they're constants. And if I do that, then I can actually diagonalize this 2 by 2 matrix, and then I get here the final potential energy surface, which is 1 potential energy surface now for the ground state. I'm just looking at the lower eigenvalue. And it has a barrier. The barrier comes basically because of this crossing. Now, if I imagine there's the upper state, which was the second eigenvalue from this mini effective Hamiltonian. Now, if I imagine to complicate things a little bit and take a reaction, this is another SN2 type of reaction, and let's say the low-level curves look like I've drawn here, the low-level diabatic curves. That is the low-level curves where I force the bonding to be such that X is bonded to C on this side and Y is bonded to carbon on this side. Right? This is a semi-artificial, but should have some chemical sense to it. And let's say that at the high level it looks more like these curves. Then what you see is that the crossing point moves around. And the crossing point was related to the barrier. So if the crossing point moves around, then I'm going to be in trouble, because now I'm going to go into this point and trying to evaluate the barrier height, and I'm going to be way too low. Yeah, basically what I'm saying is that the electronic, that the reason these 2 parabolas, first of all, these 2 parabolas are coming from the They're parabolas because a particular bonding pattern, right, has just a Lewis dot structure, a particular way of drawing those lines, has some particular preferred geometry, and they're different. And then they're going to cross at some point, and there's going to be some coupling between them, so that I'm actually going to have to diagonalize this to get the thing with the barrier. And all that I'm really trying to say is that the level of electronic structure theory I use to describe these diabats themselves, that is the shape of the potential energy surface for a given bonding pattern, a fixed bonding pattern. I'm not allowing it to, you won't get this out of the code without doing funny things, but I'm saying I'm going to fix the way the electrons are coupled. And that's going to, that can change. It could be, and oftentimes that actually will change exactly the way I've shown you. That basically the higher level will actually make it less tight, right? Because the low level, not having very much freedom, right, will try to make one of those Lewis structures very much favored, right? And the high level will say, no, wait, the electrons really are a little floppier than that, and so actually there's some polarizability. This thing actually can open up a little bit and be a little floppier. The frequencies will go down, which actually you may or may not also know that if you use very crude levels of theory, the frequencies tend to be way too high, and then they come down. It's all for the same reason. But that means that now the crossing point of those two curves is going to change, right? So the key points are, first, to understand what these parabolas really are, and second, to understand why they might change when the level of electronic structure theory changes, and third, to understand that the barrier is somehow correlated with where they cross, right? So if you buy all that, then you realize that, then I'm not saying that is all trivial to explain, right? But if you buy all of those pieces, then it's very clear that the transition state will move around when the level of theory changes, right? And move around in ways that you can almost anticipate. And that is the reason why it's very silly to go to some transition state determined at a low level of theory and then to go and spend all your money computing it really accurately. Although again, you'll find this over and over and over again in the literature, but it fails always in the same way. But it turns out, and this was actually only relatively recently, 4 or 5 years ago, figured out that the minimum energy path doesn't change very much. So what that's really telling you to do, in other words, the way in which the atoms move in going along this minimum energy path that I showed you before, going just from one well to another, that motion stays basically the same. And what really is happening is just what I showed you, that basically you're moving that point along the path. And so if that's true, you have to know that more or less from you have to have some empirical evidence to know that that's true, but it seems to be quite true. Then basically what you should do is just compute the whole path at the low level and then search along it for the maximum height at the high level, right? So now you have to do more calculations at the high level. You have to trace along the whole path at the high level instead of just doing one point, which is more expensive, but actually ends up, the accuracy of this is again sub-kilocalorie if you do it right. So basically it's by far the best way to do it. Now this whole idea that I was trying to introduce about diabats and couplings, and by diabat I just mean some potential energy surface that has some fixed electronic structure associated with it, right? Then this idea you can actually use to do something that's more or less semi-empirical, and that is, Warshall was the one that originally championed this. But basically, just say, well, wait a minute. Those little parabolas I was drawing, if I took that really seriously, then I would say, well, OH bond, if the hydrogen's connected to this oxygen, there should be a parabola. And I got the force constants in my force field, right? And the hydrogen connected to this other oxygen over here, well, that would be the same force constant, and if it's, if they're two water molecules, for example, and I actually know that too. And so, gee, if I could just take my force fields, and I could actually have one for each bonding structure, and then I could figure out how to actually build a coupling matrix element, then I could build these small matrices, and I could actually break bonds using a charm force field. And in fact, you can do this. And what's more, it's actually even better than it sounds, because you can even actually take those diabatic potential energy surfaces. If they have fixed bonding structures, then they'll also have fixed charge transfer character. So they'll be uniformly, one of them will have some ionic character will be uniformly shifted, right? So now you can actually put solvent effects into this in a way that actually is, once you diagonalize, because remember, you're going to diagonalize these curves in the end, and then they're going to shift around, they're going to actually change. And when you diagonalize, you'll get something very complicated looking. And what this is building on is the idea that maybe complicated looking potential energy surfaces really come out in large part of very simple looking potential energy surfaces that are just all coupled together, right? Which actually is quite reasonable and probably close to true. Actually, a number of people have done that for, Warshall, like I said, was the one that started it, but recently Greg Voth and Sharon Hammer-Schiffer have been two people that have really been pounding on it, particularly for water and proton transfer. So for proton transfer in water and proton transfer in proteins. Okay, large molecules directly. I mean, this is really now, these are all sort of tricks to try to do large molecules. Is there a way to just solve the electronic Schrodinger equation for large molecules without making any approximations? And there are two ways to do that. One of them is these, I've alluded to before, these sort of linear scaling or order n methods, which basically, I'm not going to go into this in detail, but basically they just take the system, and actually someone's question was directed at this. They take a large molecule and they split it up into cells, and they just say, okay, look, in this region, the cells that are really far must not be affecting anything, because, I mean, how can a wave function 10 miles away affect, I don't care what the Schrodinger equation looks like it says, they can't, right? And in fact, they don't, right? If you choose your basis set correctly, they don't. Right? So basically, you start neglecting the terms that you think are probably going to be very small because things are far away. And if you do that, you can certainly formally make something that's linearly scaling. The real question here becomes, at what point do you become linearly scaling? Because if you take 10 million times n versus 1 times n to the fifth, 1 times n to the fifth wins for a long time, right? Until 10 million times n finally crosses over and starts winning. This is the idea of a crossover point between the methods. And so far, actually, the crossover points are pretty large. They're larger than what you can do. So basically, you can't actually get much advantage from this yet. For certain types of methods, you can. For semi-empirical, where it's easier to do. They are available, however, in commercial codes. QChem is one of them. Siesta is another. Pseudospectral methods are the other way to do this, and this is very closely related to Fourier transform methods in density functional theory and wave packet dynamics, which some of you may have heard of. But the basic idea, I'll just go over it quickly, so don't worry too much about the detail. But essentially, the idea is this, is that instead of using just a basis set, let me use a basis set and a grid, which is equivalent to saying, let me use two basis sets. Now, why would I actually do that? Well, because I know that the bottleneck in all these calculations is really related somehow to these two electron integrals, which are these integrals over there shown right here. You've seen them already before, right? These electron-electron repulsion integrals. And these integrals always, this you have to play around with the methods for a while, but these integrals always are involved in sums like this, where basically you're summing over two of the indices and leaving two of the indices out. And that costs n to the fourth. There's a loop over P and Q and R and S. But if you actually put in a numerical grid, so you take this integral and you rewrite it as basically you just numerically discretize it, so that you rewrite it as some inner integral that you do analytically, and then the function value. So this is a quadrature, right? This is just taking that integral right here and making it the inner nuclear electron attraction integral, and then the two function values. And the only thing that's important here is really to notice that when you do numerical integration, you separate the indices. That's all that really matters. Because now you can take this sum and you can rearrange it in a way that actually goes from n to the fourth down to n cubed. And this is done essentially for free. The only issue is, again, a crossover. So the number of grid points that you need has to scale with the molecular size. If that scales with larger than the molecular size, you're in trouble. And furthermore, but it should, right? The number of grid points you need should basically be scaling with the size of the molecule, and it does. But there's also going to be some prefactor, and that prefactor better not be 10 million. Right? So, and in fact, it turns out that there are some tricks that involve, I think of this as a transform that I don't want to go into, but those tricks end up allowing you to actually do this with a very small prefactor. And what's important to know is that the advantage that you get then depends on the ratio between the number of grids and the number of basis functions, so the number of grid points. Right? So if the number of grid points is very small relative to the number of basis functions, then you get a full advantage of a factor of n. And if it's large, you actually lose. So that means that it's not useful, and this is the real point, it's not useful for small molecules at all, right? So you don't want to do this for anything with less than 10 atoms or 20 atoms or 30 atoms. And it's not useful with small basis sets. So you take 100 atoms and use a minimal basis set, it's not useful. What it's useful for is actually calculations that could give you reasonable answers for molecules that are on the order of anywhere up to about 300 or 400 atoms. And you can actually include electron correlation at that level. So we basically, I mean, this is the kind of system, this is like, in terms of electrons, I think this is like 300. This actually is a pretty small system for doing these kinds of calculations. We could do geometry optimizations and scan over all the spin states. This is actually a cutout of cytochrome C oxidase, is what it is. And this is iron, and this is copper. And so we could basically scan over all possible combinations of spin states of the metals and geometry optimize this and scan completely, and over all possible ligands in there, combinations of hydroxides and waters, and do this in enough time that it actually was worth doing with the pseudospectrum technique. So the only downside about all this is that it's only basically the same thing as in linear scaling. It's only available in commercial code, and that's you can get it, however, at a lot of supercomputer centers. So anyway, so this is actually an example where you can, it's something that you should know about, really, because for biological systems, when you really want to push fully quantum calculations, you can't get to a full protein yet with that, or with the linear scaling. With linear scaling, you can't even win yet. But basically, you can easily triple or quadruple the size of the molecule you can do relative to conventional techniques. So, all right, so now I want to say a few words about about quantum mechanical effects of the nuclei before we go into QMMM, which is sort of switching back to electrons. And I don't want to say too much about this, but I alluded to this at the beginning that it's not completely known whether or not the quantum mechanics of the nuclei has anything to do with anything in biology. It's just known that it's certainly yes for the case of where tunneling dominates proton transfer, which may or may not be true in any native biological systems, but it's certainly true in all cases that involve photochemistry or photobiology. And the reason is that classical mechanics only works if you only have one potential energy surface. It doesn't even know what it means to say classical mechanics if you have two potential energy surfaces. So it should happen if you imagine two potential energy surfaces. So here's an excited electronic state and a ground electronic state and some molecule which you would think of as a classical ball, but now if we're going to think of it as something quantum mechanical, it's some sort of wave packet thingy moving along. When it gets to this region, it should split into two. Because quantum mechanical things, whenever they're faced with a choice, they take all their choices, right? They never actually make decisions. So they're like, well, I could make some political joke, but I won't. But right, they never make any decision. They make all decisions. And so this is what should happen. So you should actually go from the analog of a trajectory of some sort of classical ball-like thing to two things. And every time you run into these intersections or avoided crossings or places where energy gaps are small between states, you should get a multiplication of the number of things you have. So the traditional way to do this would be to solve the time-dependent Schrodinger equation. So now we've gone from time-independent for the electrons to time-dependent for the nuclei for the nuclear wave function. And basically then you've got to solve this equation. And there are several ways to do this that are only good for like not even 10 atoms, 10 degrees of freedom, right? So like 4 atoms. And there are grid types of methods, and then there are average types of methods that are actually applicable to much larger molecules, where what you do is you average over the surfaces. So you just say you don't actually do trajectories on multiple surfaces, you just average the surfaces according to how much population there is. It's like a mean field or an average over the states. The problem is that if the potential energy surfaces are very different, so if one of them actually leads to breaking a bond and the other one doesn't, then this doesn't make any sense at all because it has some average of two things that are very different from the average, right? And that's essentially the problem with this. So that's scalable to proteins, but generally not right. So anyway, so here I just wanted, this is just what can you do? And what you can do are these spawning methods that we developed, actually. So most of what I talked to you about we didn't develop. And classical mechanics here, basically the idea is that you run a lot of trajectories, but they are basically going to be considered to be basis set. So all of these trajectories that are running, like classical simulations, will all be little wave packets, and they'll all talk to each other. And then you put in, you can basically compute, I don't want to go into details, but you can basically adaptively increase this basis set, and you can compute the coefficients that really tell you how high all these things need to be on the fly, and essentially at the sort of level of effort of maybe 10 times a normal run, right? So normal classical dynamic simulations, maybe 10 times as expensive. And we've done this, we did this actually with Klaus for bacteriodopsin. And so I'll just give you a flavor for the results. I mean, basically this is, I mentioned already that this is a protein that's going to be a light-driven proton pump. And basically that's because you have this chromophore, which is a shift base, that isomerizes after it absorbs light. And then that isomerization moves this proton, which is presumably related to moving a switch, right? It's moving the proton between two wires that are on either side. It's the easy way to think about it. So the photocycle, one of the things to know about all photobiological systems actually is that there are some fast components to the photocycle. So these are just labels that people give. And you'll notice that these labels have little numbers after them. And that's because the colors change as bacteriodopsin, actually as most photoactive proteins go through after you shine light on them. If you then probe them, you'll find that they change color, right? And change colors in ways that actually are quite easy to, are reproducible, right? And actually where it stays at 625 for quite a while, 590 for quite a while, 550 for quite a while. And so but there's usually some fast part, the sort of sub-picosecond or even say up to 5 picoseconds. And then there are slower parts. And this is the way that all photobiological systems, I think, work this way, basically because you use the photon to basically do something very quick and to lock something in, but then actually the protein has to start doing whatever it is that you gave it a kick, right? And so you give it that kick very quickly, and that's important, but then it takes the protein quite a while to actually react because it's big. So what we can do is simulate these first steps directly, basically up to a picosecond or even maybe up to 3 to 5 picoseconds. And this is the kind of thing that comes out. Basically, you get, for example, here we look at the angle that the shift-based protein, that this NH bond or NH plus bond makes with the membrane plane, and basically see that it starts out at some particular direction after I shine light on it, and then it twists, right? So you can actually get percentages of quantum yields, which are experimentally measurable, and the time scales for all of these types of events, which also are experimentally measurable, and then actually try to understand how mutating things around it would change it. So I think now I'm going to actually skip over some things and go on to QMMM. So does anybody want to ask questions about that before I go on to QMMM? Yes?
When you talk about the calculation of the larger molecule and approximation method which you use to calculate, let's say, the cytoplasmic does it mean the problem like Jaguar, they perform simultaneously semi-empirical calculations for the rest of the model or just the active side? Is it?
Oh, well, actually, no, we haven't gotten to that yet. But actually, now you're starting to ask about what programs will do QMMM types of things, I think. Oh, the answer, Jaguar will with another program called QSight. I mean, I'm not a salesperson.
The advantage to do the quantum mechanical calculation of the active site simultaneously with the semi-empirical calculation of the rest of the molecule.
Semi-empirical or force field?
Well, force field calculation. Will it be
To that, yes, of course, because the semi-empirical, the connection of semi-empirical methods with true quantum chemical methods is actually very subtle. Because remember what I told you, that basically semi-empirical methods work for reasons that you know are not related to the wave function that you're putting in, right? You know that, and so to mix that with something that's supposed to be working for the right reason, it may not be working because you don't have a big enough basis set and so forth. But now these things the errors are going to, you should not be surprised if errors amplify when you do that. And in fact, well, I mean, to be honest, I've actually thought about that quite a bit, and I still think that it can be done, but it's not straightforward, and that's the reason that it's not usually done. There may be one instance of someone trying that, but very few. To connect to molecular mechanics, then again, you know why molecular mechanics, you know that molecular mechanics works for, or you understand why it works and why it fails, and you understand why quantum mechanics works and fails, and so you can connect those together, and at least you are pretty sure that if you think about it hard enough, you should be okay, or you should be able to match.
So the Jaguar does the calculation of the active side together with the force field?
You can do that, yes. Yeah, you can. You can put in the whole protein. There's a huge advantage because if you, I mean, we'll see that actually as we go on, but if in QMMM, the whole issue, I mean, I don't think I'm giving anything away, the whole issue is the boundary, right? So, I mean, everything else is sort of boneheaded. If you understand QM and you understand MM, then what is there except the boundary, right? But the boundary is a delicate issue, and so if you can actually do a high level of quantum mechanics for a large enough system that you can push the boundary out, then you're in business. Then you're doing great, because then actually you'll be able to do the. But on the other hand, if you try to do some high level of quantum mechanics, but that means that you have to make the boundary very close, you're probably killing yourself. Then why you shouldn't be wasting your time, because the boundary effects are going to swamp everything else, right? Whatever you're spending to gain accuracy in that small region is going to be swamped by boundary effects. Yes?
Is there any way to consider temperature?
Sure, you do basically, I mean, actually, even what I showed you in terms of the photochemistry actually has temperature effects in it, because it's finite temperature, I mean, because you're doing dynamics, right? So as soon as you're doing okay. The question, by the way, was, is there any way to consider finite temperature effects in quantum mechanics? And the answer to that is two. There are two ways to do it. One way is actually to use the sort of standby, old school quantum statistical mechanics, and basically just say, okay, look, I'm going to do some force field or some force constant calculation at various minima, and then I'm going to assume things are harmonic, and then I'm going to put that into my harmonic oscillator partition function, right? And from that, I'll calculate 0-point energies. That's my first correction, and then I'll actually calculate the population of all vibrational states, and I'll compute, and I'll do thermochemistry completely right, the integral from 0 to 298 and temperature and so forth, right? And that you can certainly do, and people do that. That's well developed. There's a lot of there are a lot of books actually that will tell you how to do that, but even a regular stat mech book will. The other question though is there a way to actually do finite temperature effects in the same way that you do in classical dynamics? And the answer to that is yes. If you do, we've been talking about two things, quantum mechanics of the electrons, and in that case, if you just wrap that underneath a classical dynamics code, then you're doing finite temperature, right? And in fact, we do that all the time. I'm just not talking about it. The other thing you can do is actually, your question can also be, well, can you do quantum effects of the nuclei and the electrons together with finite temperature? And the answer to that is, again, yes, because actually what I even showed you, you have wave packet dynamics. So you have quantum mechanical nuclei, you have quantum mechanical electrons, and you're evolving in time with non-stationary states, and that's equivalent to, if you just sum those wave packets together, you're doing finite temperature dynamics. So the answer is yes, you can do that, but it's, of course, harder. It's much easier to do it the other way, which is the way most quantum chemists would do it, which is basically to do second-order expansions and statistical mechanics. And then your problem is that things aren't really harmonic. So that's what...
And you don't have to control temperature because you don't have the data to be specified.
If you're doing just electronic structure, then you're working at 0K, right? Actually, it's not even true. You're working below 0K because you don't have ZPE, right? So whatever that means. I mean, you're getting the raw potential energy surface. But as soon as you put the either harmonic approximations or real dynamics on top, then you have control over the temperature in the same way you have control over the temperature in any other simulation, right? You can control if you're doing just classical dynamics, you just control it the same way. You have a Boltzmann distribution. If you're doing quantum dynamics, then you have actually the sum over quantum states. But it's not any different from the normal case. Harder, yeah.
About that question, for some of the mechanics, seems to be wanted to simplify the revelation expectation to different level at a certain temperature and solve the revelation of the excited quantum mechanics. Is that right?
I'm sorry, please say it again.
About the temperature effect in the quantum mechanics.
Yeah,
So one can consider the different vibrational levels.
yes.
Because the temperature, there is a much effect for vibration.
You could consider different vibrational levels if you wanted to. I don't think you would want to.
Actually, you can consider
Yeah.
dynamics as different level of vibration excitation.
Sure.
That can be one way.
Sure. Sure, right. No, sure, you can do that. But actually, you don't typically, as soon as your system gets larger than 50 atoms or so, you typically don't actually want to do it that way. You want to do it averaged over everything and then basically get the temp. You want a Boltzmann average underneath, right? You're right. You can do it that way. That's perfectly correct.
Last question I have is about the electronic excited state. That necessarily use quantum mechanics. I heard about some classical method by John Corey. Maybe it's not.
That's actually not a classical method. That's you're talking about surface hopping. Surface hopping is basically I guess what you would call a semi-classical technique. I mean, the idea there is that you have, it's actually closely related to, preceded what we've done. But the idea there, the thing is that there you don't converge to any limit. It's kind of like, it's sort of, you can't, again, it's like density function theory. You can't improve your answer. You basically get an answer and that's it. You can improve the statistics, but you can't improve the answer. It's either right or it's wrong. And whereas in this case, actually, you can. You can make your answer. You can prove, and we've proved it over and over again, and it's getting kind of, got kind of boring after a while, that this converges to the exact answer. And so you can, as long as you can increase your basis set size enough, you can get the exact answer. That's as big as long has.